go ahead and take a minute to read this if you could, please. So now that we've talked about sampling distributions, we have to talk about then probably the most important theorem in all of statistics. It's kind of like the fundamental theorem of statistics. It's called the central limit theorem, and it's abbreviated CLT, and it is the foundation of inferential statistics. All the stuff we're going to do with inferential statistics, like estimating population parameters, in other words, confidence intervals, and hypothesis testing is based off this idea of the central limit theorem. So again, we're not going to look at individual values per se from a population, but we're going to look at sample statistics like the sample mean or sample proportion for samples of the same size. We're looking at distributions of these sample statistics taken from the population in samples of the same size. Now again, we've already talked about this, but we're just going to focus on sample means here. We're not going to talk about sample proportions. So what we're basically doing is we have some population where the population mean is mu. We're going to take samples from that population of the same size. Each of these samples will be of the same size. For instance, 5, 10, so forth. They're all going to be the same size. We're going to find the mean of each of those samples. And then what we're going to do is we're going to take those means, those sample means, and they are going to form a distribution that should be approximately normal under a few given conditions I'll talk about in a minute. Now, as we talked about before in an earlier slide, the mean of this distribution of sample means should be approximately the same as the population mean. It should be fairly normal. Now, the only thing that's going to vary is its spread. How spread out is it? And we'll look at that in a minute when we look at the central limit theorem, but we do know that as n gets larger, as your sample size, each of these samples gets larger, then the distribution should get narrower. Now, what does that mean? Again, if all of these samples came from samples of the size 50, we're going to have a sampling bell-shaped curve here that's taller and thinner than it was if each of these samples were of size 4 or 6 or 10 and so forth. Now, forgot to erase this. We're going to make a couple assumptions when we use the central limit theorem. Is first of all, the original population will have some mean value mu, and will have a standard deviation of sigma. Now, those values may be known, they may not be known. And also, the samples we take are going to be simple random samples, and they're all going to be of the same size n. So that's another thing, again, we have to remember. When we continue our sampling process, just as you did in class, we're going to make sure all the samples are of the same size from the population. Now, sorry, I forgot to erase all this mess, but here are the three conditions of the central limit theorem, and these are the three you're going to have to find each time. First of all, shape, and most people that talk about the central limit theorem basically just deal with how it forms the shape of the distribution. First of all, if the shape of the distribution again, we're talking about sampling means. In other words, if we're going to take samples of the same size from the population, and we're going to find the mean of each of those samples, and then we're going to graph all of those sample means on a horizontal axis, just like you did in class, the shape will be approximately normal if the original population was normal to begin with, meaning unimodal and fairly symmetric, or if your sample size, each sample was greater than or equal to 30. Now, this is important. If your original population was normal, we know it was normal, like heights of boys and girls, so forth. Any normal population, if we know the original distribution was normal, population was normal, we can have samples of any size. It doesn't have to be greater than or equal to 30. But if we do not know the original shape of the distribution, or we know it wasn't normal, like it was skewed, uniform, bimodal, non-symmetric, we have to make sure our samples are of size 30 or greater. And these two we talked about a little bit for center. The center of your sampling distribution will be which should be similar or the same as your population mean. So and by the way, this notation right here, it's called mean of the sample means. So this again, this mean, this symbolization right here means mean of the sample means. It's a mean of a sampling distribution. It should be the same as the population mean. And then the spread, this is what changes. The standard deviation of the sample means, how spread out is our sampling distribution of sample means, is equal to your population standard deviation divided by the square root of the sample size. Okay, so I'll say that again. The standard deviation of all your sampling means of your sampling distribution should be equal to your population standard deviation divided by the square root of the sample size. So as n gets larger, this whole value gets smaller and then your distribution gets narrower. Now, this is important. We sometimes refer to this here as the standard error of the